Welcome to the Log Lover's Guide to Derivatives. In this video we consider the relationship between the logarithm and derivatives. And in particular we consider two things. One is the derivative of log, well actually both, so natural logarithm ln x and also log to a general basis b of x. But then we move on and use something which is called logarithmic differentiation. It sounds really scary, but actually it is meant to be a method to differentiate complicated functions. So if you have a complicated function which might be difficult to differentiate otherwise, then the logarithmic differentiation is often an easy way to get around it. So I hope I made you a bit curious, so let's move on and look at these things. Now the derivative of log is already a challenge. So let's start with the natural logarithm ln. To differentiate this, we use implicit differentiation for the inverse function of log, right? We know the inverse function of log is the exponential function. So we have e to the y equals x, right? Y equals log x, so e to the y equals x. And we understand this y to be a function of x because we are interested in the derivative dy by dx. So really, then we should read this as e to the y of x equals x. And then we use implicit differentiation, which means we differentiate that equation by x. So we write d by dx of e to the y of x equals d by dx of x. So I just wrote it down, applying the derivative. But then on the left-hand side I have a chain rule, right? The outer function is e to the and the inner function is y. I differentiate the outer function, which is e to the y of x, times the derivative of the inner function, which is dy by dx. On the right-hand side, we have the derivative of x itself, which is 1. So then from this we get dy by dx equals 1 divided by e to the y. And now I leave out the argument x because we all know that y depends on x. So it's 1 over e to the y. But 1 over e to the y is, according to this guy, this is 1 over x. So we can write this to be 1 over x. So cool. So we find already a formula for the derivative of log. So then we get d by dx of log x equals 1 over x. Actually, this is a rather useful formula, a very important formula, in fact, which you should try to remember. So this is the natural logarithm, and the formula looks rather easy. Let's look at the logarithm to a different base. So here we have log to base b, and again I use implicit differentiation. I write, first of all, b to the y equals x, and then I differentiate d by dx of b to the y equals d by dx of x, which is 1. Now I need to use a formula which we have derived in other contexts earlier. D by dy of b to the y equals b to the y log b, and now it's a natural logarithm, so ln b. So this is exactly the left-hand side, so then we get by ln b times the inner derivative. The inner derivative is the y derivative, so times dy by dx, and then the 1 is unchanged. But so then we can solve it for dy by dx, which then is 1 divided by b to the y log b, but b to the y has been x all along, so then this is also 1 divided by x log b. So then for the logarithm to a base b, we find that d by dx log bx equals 1 divided by x log b. And now you see, if you compare this with the natural logarithm, which says d by dx ln x is 1 over x, the only difference is the log b in the denominator. So there's another reason why the natural logarithm is so cool, because you don't need to worry about additional factors of log b in the denominator. So this is the simplest form of all these possible equations. Let's look at this example. Y equals ln of x plus 3 divided by x minus 1. To differentiate this, we use the chain rule, where the inner function is u of x equals to x plus 3 divided by x minus 1. So then we differentiate this function d by dx of the function y of u of x. So this clearly is a chain rule. So we first use the derivative of y and then multiply the inner derivative of u. So this is dy by du times du of x by dx. Y of u is just ln u. So the derivative of this is 1 divided by u. So we have 1 divided by u, and then times the derivative of u itself, which is a quotient rule. For the quotient rule, we use low d high minus high d low, draw a line and square below. Low d high, low, x minus 1, derivative of the numerator is 1, minus high d low, x plus 3, derivative of the denominator is 1, divided by x minus 1 squared. And then this 1 over u, this first term here, now I use the formula for u. This is x minus 1 divided by x plus 3. And in this large fraction I can multiply it out, so it is x minus 1 minus x minus 3 divided by x minus 1 squared. And then several terms cancel, so the x cancels with the x minus 1 cancels with the square from here. And so then we continue and we get minus 4 divided by x plus 3 times x minus 1. And another example. Let's say y is equal to log of absolute value of x. So what is this? This is the log x if x is positive, and it is the log of minus x if x is negative. So now we differentiate piecewise. So we first differentiate the positive bit. So y prime is then 1 over x if x is positive. So far so good. If we differentiate the other part, then we have log of minus x, so we have multiplication with minus 1 in the argument of log, which can be seen as an inner function. Then by the chain rule, this is minus 1 divided by minus x for x less than 0. So here you might stop the video and just try it yourself, if you get this case yourself. Okay? And so then this is 1 over x for x positive, and this is 1 over x for x negative. Oh, this is cool. So we get the same expression, no matter if x is positive or negative. And so then here is the other important formula which I promised. d by dx of log of absolute value of x is 1 over x. Now, this is a formula which we'll use all the time. So I recommend you to memorize it, to put it in your memory bank. Let's come to the second topic of this video, which is logarithmic differentiation. It is used to make complicated derivatives easy. So let me show you how this works. So I give you a complicated example because this is of course what it's made for. So let's look at y equals x plus 1 squared times e to the 3x squared plus 9. So if you have to differentiate this, well, you need a chain rule, and then this time this you need a product rule, and then you need the exponential with a chain rule, and you need a derivative of this one. So it is what I would call a complicated integral. So let's log transform. So we log y is then of course log of all that. So then we write this as log of x plus 1 square plus the log of the exponential bit, 3x squared plus 9. And now we use another log rule for the exponent, so then this is 2 times log of x plus 1 plus 3x squared plus 9. Now look at this new function here. I think this looks rather easy to differentiate, right? Log differentiate is 1 over x. 3x squared differentiated is of course super easy. It's 6x. And 9, the derivative of constant 9 is 0. So let's do that. So then we do d by dx of log of y of x is, we keep the 2, We differentiate log, so we get 1 over x plus 1 times the inner derivative, which is 1, plus 6x, and that's it. That's it. So come on, this is easy. However, we also need to look at the left-hand side. So d by dx log of y of x is 1 divided by y times dy by dx, chain rule, right? So this means we now have to equate those bits. So this equals that. Giving, so then we have dy by dx itself, this is what we are looking for, equals y times 2 divided by x plus 1 plus 6x. So, final step, we have to substitute what y really is. And y is given on the top, so this is x plus 1 square, e to the 3 x squared plus 9, and then all this times 2 divided by x plus 1 plus 6x. Yeah, I didn't promise you a nice formula, but I promised you it is possible to get a formula. So here's a derivative of that function. It is complicated, but the log really helped us. It made life easier. So let me summarize. We have here 3 formulas for the derivative of the logarithm. The first one is d by dx of ln x is 1 divided by x, and actually d by x of ln of absolute value of x is also 1 over x. These are important formulas for the natural logarithm. If you do not have the natural logarithm but the log to base b, then you get an additional factor of log b in the denominator. Of course, you know that log to base e is exactly ln. So we could use this general formula for the ln as well. And then you see what happens, right? Then we need to take the ln of the base, which is now e, and ln of e is equal to 1. And so then we have a connection directly from this formula to this formula. Now for logarithmic differentiation, if a derivative is hard to compute, then transform it with ln and see, maybe it's easier. Log differentiation is absolutely necessary for functions of the form f to the g of x. I have not done an example here. Maybe we do examples in class. Functions of this form can easily be differentiated using logarithmic differentiation. Low d high d low, line in the middle, and then you square whatever remains from the bottom. Low d high minus high d low, and then something in the denominator, which is the square of the x minus 1 term. Low d do, d high d die d, hiddly doodly, d diddly doodly die. Schnaddly doop deep bap boom boom bam boom doop dap dap, the schnabbly dab 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 dab.